The most dangerous application failures do not announce themselves with a blaring red console error. Instead, they are completely silent. A browser tab freezing or a sudden memory spike typically indicates a structural collapse. These occur when unhandled type mismatches compound, or when detached data starves the system of available memory. To prevent these crashes, legacy development relied on defensive barricades, deeply nested if statements, manual type-of checks, and long chains of Boolean logic. This volume of defensive logic creates risk. The code expands vertically, obscuring where memory leaks originate. Modern JavaScript provides a concise alternative. Destructuring and optional chaining provide a new execution path. They enable predictable extraction and memory safety, bypassing errors without manual validation. Understanding how this syntax executes under the hood allows a developer to predict how an application will behave when it encounters unexpected edge case data. Consider a deeply nested JSON payload arriving from a backend API. The client environment must ingest this data without holding the full, unnecessary payload in active memory. Destructuring extracts only the necessary data points. By specifying coordinates, the engine isolates those values. Executing const a_b_rest equals obj detaches specific nodes into an isolated memory block. The rest operator then sweeps remaining data into an independent container. This extraction logic contains a common trap. When using the spread operator to duplicate an array, it is easy to assume you have created a completely isolated clone. The spread operator executes at an O of n time complexity. It iterates through the structure, but it only copies the top-level references. The nested values remain untouched. If an array contains an object and you use spread syntax to clone that array, the engine duplicates the pointer, not the object. Both arrays now point to the exact same mutable memory address. Modifying the object in the second array will alter the original. This shallow copy limit is a primary source of state corruption in complex applications. The JavaScript engine applies similar mechanical parsing to string creation and data injection. Standard template literals evaluate variables and concatenate them directly into a raw string. It is a direct merge of data and text. Placing a function name before the backticks converts this evaluation into a hidden function invocation called a tagged template. The parser intercepts the input before it is evaluated. The engine separates static text from dynamic interpolated values, storing them in distinct arrays. The tag function receives both, validating or escaping dynamic values before assembling the final DOM output. This intercept is how GraphQL and styled components safely parse domain-specific languages. It moves the security check to the parsing stage, blocking injection attacks before they reach the browser. Even with sanitized data, applications frequently fail during traversal. Attempting to read a property on an object that the engine evaluated as undefined will stop the main thread. Execution logic requires a continuous, unbroken path. An unexpected gap in the data structure causes a violent failure that stops everything. In a chain like user.profile.settings, if the profile object is missing, the engine throws a type error. Optional chaining provides a built-in abort sequence for these missing nodes. Adding the question mark enables short-circuiting. The moment the engine encounters a nullish value, it instantly halts evaluation. The engine safely returns undefined for the entire expression, bypassing the error that would otherwise crash the application. When data is missing, we often assign fallback default values using the logical OR operator. However, the logical OR evaluates based on Boolean truthiness. It will flag a valid 0 or an empty string as false and overwrite them with your default value. Nullish Coalescing provides a strict evaluation. It ignores Boolean truthiness entirely. This operator triggers only on null or undefined. This allows deliberate zeros and empty strings to pass through, while still providing a safety net for missing data. Using these tools together shifts application logic from reactive error handling to defensive traversal. Preventing crashes is only the first step. Long-running applications must also manage where data lives, the memory heap. Standard objects are frequently used as maps to link keys to values, but objects can only use strings or symbols as keys. If you use an object as a key inside another object, the engine coerces it into the string object, destroying the original memory reference. The map class solves this by maintaining precise memory identities, allowing complex objects as direct keys. But the map class introduces a memory risk. It holds strong references to its keys. JavaScript clears memory using a mark-and-sweep garbage collection algorithm. The engine will not delete an object if a strong reference still points to it. If an item is tethered by a strong reference, the automated mechanical sweeper cannot remove it, leaving it permanently taking up space. If you cache a DOM node in a standard map and then remove that node from the screen, the map still holds a strong reference to it. This creates a permanent memory leak. WeakMap and WeakSet are designed to hold state without interfering with garbage collection. A WeakMap tracks an object using a weak reference. This connection does not count toward the mark-and-sweep survival check. When the application deletes the DOM node from the interface, the garbage collector ignores the weak reference. It clears the object and frees the memory automatically. Mastering weak references allows for the creation of massive, single-page applications that can run for hours without exhausting the system's memory. These features represent a cohesive methodology for handling data in modern JavaScript. We see the difference when comparing legacy logic with modern refactors. Destructuring unpacks data without cluttering memory. Short-circuit operators allow the engine to traverse it safely. And weak maps ensure data is removed from the heap when no longer visible. Scaling an application requires a clear understanding of how the V8 engine interprets, allocates, and deletes this data. Understanding these engine-level mechanics allows you to build interfaces that remain stable and performant, regardless of the scale of the data they consume.